So even though I'm doing this experiment in year 8 at the moment, it's important that the year 12s also, year 11s and 12s also watch this, because you need to get some of the info here that you might not get elsewhere. So first I break it up, and I use a sieve and bake it up into 3 different sizes. And for this experiment, what we're meant to be doing is collecting the gas through the measuring cylinder here and displacing the water. And I'm going to do a gravimetric method, but the year 8's going to do this method. So this one's fine, just like the diagram says. Just make sure that the gas is not soluble in water, so it's not both small and polar. All the gases do dissolve in water a little bit, but some are highly dissolve in water quite highly. And so the best method, I'm going to use a gravimetric method, and I'll point out some errors with that as well. The best method would be this, using a glass syringe, which has not a plastic one. This one has virtually no friction on it, so that's not resisting and causing any inward pressure. And then the big issue with all of these is the escape of gas. And so we do have these things called a dropping funnel, and this one's especially good because if you just have it has that little side arm there, so that the liquid displaces the gas, doesn't push the gas further into the tube, but there's no net change in volume. So this is quite an advanced dropping filter, and you could have another hole in the bung up there, so that there is at no point is there an opening for any gas to escape, and all the gas change goes into the syringe. So that would be a close to perfect setup that I've never seen someone do. So just letting you know. Okay, so what I'm doing here is a gravimetric method. And so I put about 1 gram of the 3, and then I put 10 mils of the liquid in there. And then it bubbles off. And this one, you can do gravimetric methods as long as the gas is heavy. So carbon dioxide gas is heavy, but if you did this with something like acid plus metal, it gives off hydrogen gas. It's too light and you're not going to get a reading. And so the other fault with this is, the carbon dioxide gas is heavy, it comes off and I do get readings. But because it's a heavy gas, it actually stays inside the beaker. And the only gas I'm losing would be the gas that's overflowing outside the beaker. So that's a fault. Another fault is this, it's only to 3 decimal places. You really need a Mettler balance. So they're errors I didn't discuss at the end as a summary. So I just want to look at the data here now. So for junior science, we're just doing average rates, which is fine. But the problem with doing average rates is you don't actually, as the reaction progresses, for this one it heats up and the concentration decreases. So you're not controlling your variables. The only time the variables are controlled at the very start. So this one here, this orange one, there seems to be an anomaly with that. This is what you're expecting. You're expected to be very quick at the start, and then the rate to slow off as you run out of reactants. And so if you did an instantaneous rate, you do the fastest rate. So that would be the fastest rate. So you measure the gradient over that line, delta y and delta x. So the change in mass over change in time, that's the rate. So that's the rate of reaction for that instantaneous. If you're doing an average, they're usually slower. So if you're doing an average rate, you'll just take the gradient from 0 to 30, and you can see it's less steep. So that one's more steep, that one's less steep. These ones just pretty much instantaneous, don't make a big difference here. They're pretty much because it takes time to react. So actually in this case, because the data is so poor, an average rate's probably better. And so you can see that the larger and then getting smaller, the smaller ones are faster after 30 seconds. So the real issue with that is I don't have a range of 5, so I can see the relationship, but sometimes it's not so clear. And then a repetition of 5 also, so that I can get rid of the anomalous results, like possibly this one, so I can have a better idea of my precision and do an average, so I've got a better accuracy. So just to finish off, just a quick explanation on the collision theory, so why this actually works. So what you have is you have a large particle that's 2 by 2 by 2, Well, it's 2 by 2 is 4 centimeters squared, and there's 8 sides. 2 by 2 is 4 times 6 sides, 1, 2, 3, and then 3 at the back. So that's 24 centimeters cubed. So that's made up of 8 blocks, and each block is 1 by 1, which is 1 centimeter squared, and then 6. So that's 6. So 8 by 6 is 48. So the smaller is, you got double in this case for just this comparison. So you can see the surface area increases. So if you have more surface area, which is this calcium carbonate solid here, that the HCl particles have more places where they can collide. And so in a funny way, it's sort of mixed better. But we don't say mixture, we say surface area. And so if there's more places to collide, then there's going to be more collisions. So number 2 is energy. Number 3 is 3D orientation. So when you have more collisions, then you're increasing the probability that it will collide with enough energy, and you're increasing the probability it will collide in the correct 3D orientation. So that is the collision theory explanation of why surface area increases the reaction rate. And just lastly, just to follow off, I think the main improvements to the experiment would be always at senior level, range of 5, repetition of 5. Yeah, you can get away with what we did there for junior science. Instantaneous rate instead of average rate. Almost never do average rate for senior. You can do that for junior, that's fine. But you've got to realize there are errors there because you haven't controlled your variables. And probably even a little bit too advanced for seniors is a glass syringe and dropping funnel. To this point in time, I still haven't had a student ask for it, so I haven't seen it done.